kesejahteraan masyarakat. BRIN juga mendorong riset dan inovasi menjadi ekosistem di Indonesia yang maju dan berkembang dengan dua sasaran utama. BRIN menyadari potensi luar biasa putra-putri bangsa dalam bidang ilmu pengetahuan dan teknologi. Untuk itu, berbagai kebijakan riset dan inovasi diarahkan untuk menghadirkan kompetensi SDM iptek terbaik. Menghasilkan berbagai program unggulan sebagai bentuk komitmen BRIN terhadap periset, inovator, serta masyarakat luas dari berbagai disiplin ilmu di seluruh negeri. Peningkatan kualitas ekosistem riset dan inovasi di Indonesia juga tercipta melalui kolaborasi dengan berbagai kementerian, lembaga, industri di dalam negeri, dan pemerintah daerah, di antaranya dengan dibentuknya Badan Riset dan Inovasi Daerah atau BRIDA. Selain itu, kerjasama dengan berbagai lembaga riset di luar negeri juga terus didorong melalui partisipasi aktif sebagai anggota dalam berbagai organisasi dan forum internasional. BRIN menata alur riset sehingga lebih efektif dan efisien dengan mengintegrasikan sumber daya manusia, infrastruktur, dan anggaran dari berbagai lembaga litbang jirap. Berorientasikan prioritas riset nasional, BRIN melakukan evaluasi secara komprehensif untuk setiap percepatan yang tengah berjalan. Upaya tersebut didukung melalui pengelolaan berbagai fasilitas riset dan inovasi yang tersebar di 17 provinsi di Indonesia dan akan terus bertambah mengikuti perkembangan kemajuan iptek. BRIN terus meningkatkan kontribusi riset dan inovasi terhadap pembangunan nasional melalui pembangunan dan revitalisasi 4 kawasan sains dan teknologi atau KST. Sebuah kawasan terintegrasi berupa fasilitas laboratorium riset, laboratorium pengujian, fasilitas industri, baik startup maupun UKM pada skala kecil atau uji coba, ruang kantor tenan, coworking space, ruang pertemuan, ruang pameran, dan fasilitas pendukung lainnya. BRIN hadir untuk mewujudkan cita-cita menuju Indonesia Emas 2045. Melalui konsolidasi sumber daya iptek, menciptakan ekosistem riset, dan fondasi ekonomi berbasis riset. Menjadikan Indonesia sebagai rujukan dunia dalam pengembangan dan pemanfaatan ilmu pengetahuan dan teknologi, kebijakan, serta kemanfaatan bagi umat manusia. Alam adalah sumber inspirasi. Ilmu adalah fondasi. Dan mengamalkannya untuk kemajuan bangsa.
Can you hear my? Cek.
Oh, aku bukan ORNAMAT ya? Iya, benar-benar. Karena saya cari.
Okay, good morning, everyone.
Good morning.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Welcome to the 53rd ORNAMAT, bi-weekly webinar organized by Research Organization of National Technology and Materials. So I would like to introduce myself. My name is Evi Indari. I am a postdoctoral researcher at the Research Center for Quantum Physics. And on this occasion, I will be moderating this webinar. And before starting the event, I would like to read the agenda for this morning. So, but prior the event, may I ask your cooperation to use the virtual background attached in the chat column? Ya.
Suaranya agak putus-putus, Pak.
Okay. I would repeat in Indonesian. Saya harap kerjasama dari Bapak Ibu sekalian untuk menggunakan virtual background yang sudah disertakan di chat column. Okay. And for this morning agenda, before starting the main event, we would have an opening ceremony, including the national anthem and taking picture together. And for starting the event, let's start with singing the national anthem. Jadi Bapak Ibu sekalian, untuk memulai acara hari ini, mari kita menyanyikan lagu Indonesia Raya terlebih dahulu. Dimohon untuk bersiap-siap. Apakah sudah siap, Bapak?
Siap.
Alright, thank you very much for everyone. Terima kasih Bapak Ibu sekalian. Untuk selanjutnya kita akan mengambil foto bersama. So for the next agenda, we will take our picture together. So please open your camera. Ya, untuk Bapak Ibu dimohon kerjasamanya untuk membuka kamera. Ya, silahkan dimulai.
Oke, slide pertama. 1, 2, 3. Oke, cuma ada 1 slide ya Bu ya.
All right. Thank you very much.
Nanti berikutnya akan menyusul, saya ambil lagi.
Okay. Yeah. So I've said that for those who have not yet used the virtual background, I would like to kindly ask your favor to use it, as it's already attached in the chat column. Thank you very much for your cooperation. And now we are moving to the next agenda. That is the opening remark from our head of research organization. But before that, as usual, it's a rhyme time. So I will read a rhyme. Okay. Explore Japan by a subway. Get a fresh sushi in the morning. Hello everyone, how are you today? Are you ready to start learning?
Yes. I'm
Yeah.
fine.
I hope we all are
Tanyakan
ready
apa
to
kabarnya?
start learning. And then next, we'll have the opening remark from our head of research organization, Professor Ratno Noryadi. Thank you. For Professor Ratno, please, you can start.
Terima kasih Mbak Evi. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sehat, salam sejahtera untuk kita semua. Good morning, ladies and gentlemen. On behalf of the organizing committee, Research Organization for Nanotechnology and Material BRIN, I would like to extend warm welcome to all participants joining us for the 53rd ORNAMAT webinar. So today we are excited to explore ORNAMAT webinar with the expertise of our 2 distinguished speakers. Those are Professor Hiroyasu Matsura from Tokyo University, Tokyo Daigaku, Japan. He will present the research result entitled of thermoelectric effect derived from various heat flows. And the second speakers will be Dr. Dita Puspitasari from Shibaura Institute of Technology, also from Japan. She will present about the doped organic superconductor and magnet probe by muon spectroscopy. So Dr. Dita, now visiting researcher and Research Center for Advanced Material, Research Organization for Nanotechnology and Material. So we are also grateful to our moderator, Dr. Evi Dwi Indari. She is the postdoctoral researcher in Research Center for Quantum Physics. So she will guide us in this ORNAMAT webinar and today's discussion. So, again, thank you very much for our speakers and moderator for their contribution, and to all of you, all participants, for being here in this webinar. We look forward to the valuable insight our speaker will share, and hope this session foster meaningful discussion. So thank you for being here, and let's make the most of this opportunity to learn to learn and connect. So finally, I also would like to close my welcome speech by pantun, but I'm sorry, my pantun in Indonesian language, not in English. Oke, nasi merah dimakan hangat-hangat. Pakai ikan goreng rasanya pasti lebih nikmat. Untuk semua hadirin yang terhormat, kembali kita hadir menyaksikan ornamat. One more. Anak kecil memanglah lugu, terkadang bawaannya emosional dan tidak malas. Inovasi terbaru selalu kita tunggu-tunggu untuk pembangunan ke arah Indonesia emas. Thank you.
Keren.
Enjoy this seminar. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Ratno, for the opening remarks. And now let's move to the main agenda of this ORNAMAT 53rd. We have two speakers, special speakers, in fact, because they are living in Japan. And the first speaker is Professor Hiroyatsu Matsura. Some of you might know him already from yesterday's talk. We already delivered an introduction lecture yesterday. So his education was started in Osaka University, Japan, and then he's employed in University of California, Riverside in March to May 2010. And then he was a researcher in Osaka University, and then now he's an assistant professor at the University of Tokyo. And his talk would be the thermoelectric effects derived from various heat flows. And Professor Matsura, so your time is 30 minutes. Yeah, before finishing, if there is 3 minutes remaining, I will give you this time. 30 minutes. Okay. You can start. Yes.
Okay, thank you very much for giving me a chance to talk in this meeting. So I'm Hiroyatsu Matsura from University of Tokyo's Department of Physics. So today I'd like to talk about some electric effects deriving from various heat flows. So yesterday, okay. Okay. どれだthis one. This one. This one. This one. Yeah. This one. Yeah. Okay. No problems? Okay. I see. Okay. This one. This one is one and slide show. Maybe okay. This 지금 no. So okay, so そう。あれ、これは、ちょっと待ってよ。I'm sorry, I have wrong. Wait,
The second one.
second one, this one?
Yeah, this
This one.
Yeah.
That's one.
What about?
Ya, ya.
It's good.
Oke.
Maybe, yeah. Maybe if you use a slideshow, maybe I have troubles. It's okay. Okay. So, that not change this one. Got it. So it's just a little confusing.
Professor Matsura?
Yeah, I'm sure I have troubles. ちょっと待ってよ。
Change your slide.
Yeah. I have several. Okay. This one is this one. Okay.
I'm sorry.
On to. あれ
Could you
あれわかんない。
fix this one?
This one? Okay.
Yes, and then this.
Okay.
Then you can.
But I cannot. Okay. I can. Thank you very much. Okay. Thank you. Thank you. Thanks. Can you share this?
Professor Matsura, you can start.
Okay.
You can,
Okay.
sir, you can sit down if you like.
Okay.
Coba jadi bisa lihat orang lain.
Yeah.
Okay. So today, yesterday I showed this slide. So University of Tokyo is here, located here, so center of Tokyo. And if you like the Tokyo, please come to Tokyo. Very welcome. So, and today's seminar, I talk about these topics. Yeah, yesterday I already talked most part, but today I talk about the detail of theoretical point, theoretical part of thermal effects. The first one is I talk about what is thermal effect, but this one, yes, I talked yesterday, but I talked a little, and then so I talk about the relationship between the theory and societies, and then so I talk about the theoretical studies of the thermal effect. And then if I have a time, so I talk about the recent study of the thermal effect in film substrate systems. So maybe you remembered yesterday's seminars. So this is
Can you just see the camera because you can show the audience in the other.
camera.
You just when you do the presentation, you just show the.
Okay.
So the other can.
Okay.
Yeah, that's a request.
Okay. Thank you. Can you share this?
Yeah.
Okay. Okay. So
Now please share.
can you share this?
You need to share.
Oh, I see. Okay.
Yes.
This one. This one. That's which is right. This one. First one. Okay. Really can go.
Yeah, the problem is remaining. First share.
I'm sorry.
That one. Yeah. I think it is better now, right?
Now okay.
Can you take this?
It's now okay.
Yeah, now.
Okay. Okay. So this is firstly I talk about the thermal effect. So this effect was found by Zevik 200 years ago. So this one is a schematic cast that not works. 設定かな、表示設定。これでどうだ、ダメだ。失敗。I'm sorry, I have some problems here. ちょっと待って、this one?
Yes,
And then, pointer.
I think we want to.
This is okay. Okay.
It's like.
Okay. Can you share another one?
Share. I think the green one.
Green one. Green
Yes,
one.
yes.
This one. This one.
Okay. Now
Okay.
the problem is now
Oh.
it is not extended, but it's mirror.
I see. Oh, sure. I have no idea.
Unplug and then plug the HDMI first.
Okay.
Unplug and then plug it again.
Okay.
Sorry. Okay. Mas Edi, ini sekarang bukan extended tapi double. Oh, right.
No problem.
I think it's
It's okay.
okay.
It's okay. 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 I'm sorry. I have many troubles.
No problem.
Okay, so I have many times, much times. Okay, so this is a Zeybek effect. Maybe you can see that this YouTube videos. So, if we make the temperature gradient in this device, we can use this plane. This plane called Shinkansen. This is a very famous in Japan. So, high-speed planes. So we can use this thermal effect by using by moving the Shinkansen. So Zeybek coefficient is defined by these equations, and Zeybek equal the voltage over the temperature gradient. This is just the definition. So when we apply the temperature gradient like this, this is the hot side and this is the cold side. In this case, we can get the temperature gradient, and then so finally we can get the voltage in this direction. So okay, I skip this one. So the important point is the efficiency of thermoelectric effect. The efficiency is expressed by these equations. This equation is coming from the two parts. The one part is the kernel efficiency times the additional part. So additional part is coming from the dt. So dt is called the dimensionless figure of merit. So this gt is determined by the material properties. So this is the temperature dependence of gt. So these material are potential material of some electrical device. So the amplitude of gt is around 1. 1 is a very how to say, it's a good amplitude. But the maximum is around 2. So we need to increase this gt to get the large efficiency. So the highest efficiency, recent highest efficiency is around 8. So 8 is a very large efficiency, but we need more. I mean, we need to increase this efficiency more and more. How to say, yeah, to get a good thermoelectric device. So okay, I skip this one. So today's talk we focus on the theoretical part. So especially we focus on the theoretically in thermoelectric effects. So we have 2 theoretical studies. One is band engineering. So this band engineering is how to say, is just a prediction of the thermoelectric property from first principle calculations. So in this case, we focus on the heat flow from electron. Mainly, we focus on this heat current. And recently, we discussing about the how to say, the machine learning method to get the thermoelectric properties. And second one is how to say, basic. So we discussing about the basic concept of thermoelectric effect. The key point is that what kind of heat flow is there in solids, and what kind of thermal phenomena do various heat flow cause. So this is important to get the new thermal materials. So especially in this talk, we focus on the second ones. So, but firstly, I talk about the basic concept of thermal effect. So I talk about so here I talk about the basic concept of the linear response. So when we apply the external field, we can get the flow. For example, we apply the temperature gradient. In this case, we can get the heat flows. So maybe you know that this is an Ohm's law. If when we apply the electric field, we can get the electric response. This is derived from the firstly derived by the Cavendish, and this is famous as Ohm's laws. But maybe you know that the Fourier's law is just these equations. When we apply the temperature gradient, we can get the heat flows. But this equation does not relation between, because this is an electric field and this is a thermal gradient. So this is different external field. But we have the Zeebeck effect. Zeebeck effect is this is cross effect, combined effect. So when we discuss the Zeebeck effect, we need the cross term. So this means that we can express these equations. So we have the cross terms, this L12. L12 is corresponding to the cross terms. So when we apply the temperature gradient, in this case, we can get the electric field. And then so when we apply the electric field, we can get the heat current. This is cross correction. So Zeebeck coefficient, by using these equations, Zeebeck coefficient is defined by like this. So when we have the in this conditions, JE means that the electric current is zero case. By using this equation, we can get the electric by the temperature gradient. The Zeebeck is defined by this equation. Therefore, that we can get the S equal L12 over T L11. L11 means that electrical conductivity. L12 means that the cross correction. So namely, Zeebeck is expressed by these coefficients. And then thermal conductivity also, we can get these equations. So this equation also has a L1, L22, and L12, L21, L22. L22 means that this coefficient, and L12 is this one, L21 is this one, and L22, I'm sorry, this is L11, L11 is this one. So, and the power factor is like this, and ZT, I talked the previous slide, is defined by this equation. So important point is that if we know that we know L1, L12, L11, L12, L21, L22, in this case, we can calculate the Zeebeck, kappa, and power factor and ZT. This is important point. So therefore, we need Lij. So to get the Lij, theoretically, we use the Boltzmann's equations. So this is the Boltzmann's equations. So this, the right-hand side, we have the two terms. This is coming from the temperature gradient, and this is coming from the electric field. And I'm sorry, this is the left-hand side. The right-hand side is coming from the collision terms. This is the origin of the dissipations. And using the, for example, the reaction time approximation, we can get this one. So this equation means that this F is the distribution function in the steady state, and F0 means that the distribution function of equilibrium state. This is corresponding to the Fermi distribution function in electric case. And we have the additional terms. Additional term is coming from the temperature gradient and the electric field. So using this equation, we can derive the electrical current and thermal current like this. And comparing from this equation, we can get the L11 and L12, L22, L21 like this. So using this equation, we can summarize this equation. So important point is L1. This equation can expressed by the same sigma. This sigma is coming from these equations, and V is the velocity of electrons, and tau is reaction time, and delta is just delta functions. So if you know this sigma, the function of sigma, so you can calculate L11, L22, L2, L12, and you can get the Z coefficient, and then you can get some conductivity, and you can get the ZT. So the band structure, band calculation can give the information of V and epsilon k. So if you use that, for example, the constant tau, you can get the sigma, and then you can use this equation, so you can get the L11, L12, L22, and you can get the Z coefficient. This is how to say, this is band engineering studies. So recently when we calculate this sigma, we need the tau, but the band calculation does not give the tau directly. But recently we make a new method to obtain the sigma, this sigma. So from the experimental result. So yeah, we made a new method to obtain sigma by machine learning and the experimental result. The schematic picture is like this. So usually we use this equation to calculate the sigma, and then we use a band calculation, and we can get the sigma, and we can get the L11, and so finally we can get the sigma and electrical conductivity. This is the theoretical driven study. But by using the machine learning and experimental result, so data-driven study, by using data-driven study, we can get this sigma. So this is a first, this result is the first trial result, and by using this this experimental result, and by using data-driven studies, we can get these sigmas. So using this one, so we can predict of the temperature dependence of the Zebek, for example, so without band calculations. And then so by comparing the band calculation, we can get the tau directly. This is a new method. So we made this method. So next I talk about the simple study of the metals case and semiconductor case. So using these equations, so we call this equation Zomma-Feld-Beatty relation, because so Zomma-Feld-Beatty firstly derived these equations, so 1930s. So therefore we call this equation Zomma-Feld-Beatty SB relations. So by using these equations, so Zebek is by using the Zomma-Feld expansion, so we can get this equation. This is called mode relation, mode formula or mode relations. And then by using the constant tau, we can get this equation. So the important point is Zebek is proportional temperature dependence, proportional to T. T is the temperatures. And the amplitude is around 1 microvolt per Kelvin at 100 kelvins. So when we compare the experimental result, so yesterday maybe I showed this experimental result. This is a experimental result of the gold, copper, gold, silver case. So using this equation, we can write these lines, but we have the additional terms. So what is the origin of this additional term? Around here is okay. This is linear dependence, but we have the deviation from this equation. So we have the extra contribution in some effect. So the next I talk about the semiconductor case. So using these equations, we can get the Zebek. So yesterday I already showed that this equation. So in semiconductor case, Zebek is expressed by this equation, and the amplitude is around 1 millivolt per Kelvin. At, for example, the 50 kelvins, and in the silicon case, phosphide doped silicon case around here. But this is an experimental result. So the blue lines corresponding to the N-type sequence, low doped case, and this is a germanium case. So we have this dotted lines corresponding to these ones, and we have the deviation from the experimental theoretical result. Yeah, we have the additional term. So the important what is additional terms? So what is the origin of the additional term? The origin is the Honnold. So when we apply the temperature gradient, we have the this figure shows that this is hot side, This is cold side. And in this case, the electron move from hot side to cold side. And then finally, we can get the voltage. This is the usual imaginations. But when we apply the temperature gradient, we have the additional heat flow. So this means the Honan, we have additional heat flow is coming from the Honans. So Honan also the origin of the heat flow. So if we have the heat current of Honan, and when we use the interaction between the electrons, in this case, we have additional the electrical current by of electrical current like this. So by using the Honan, heat current of Honan. So this the heat flow of Honan so induce the flow of electrons by electron-Honan interactions. This is Honan-Black effect. So the Honan-Black is a universal effect. So because there are many materials to show the Honan-Black effect. This is the metal case, this is the semiconductors, and metals, graphite, carbon nanotube also shows the Honan-Black. The important point of Honan-Black is that they have large power factors. For example, the iron antimony 2 has a very large power factor, 550 millivolt per Kelvin. This is the temperature dependence of power factors. So these material are potential material of some electric device. So iron antimony 2 is located here. The power factor is very, very large comparing from the other materials. So therefore, the Honan-Black is focused on the some device, especially in the low temperature region. So the essence of Honan-Black is, okay, in the metal case, Honan-Black is expressed by these equations. So Zbig is proportional to the specific heat of lattice. This CL means the specific heat lattice. So maybe you know that the specific heat lattice is proportional to T cubed at low temperature. Therefore, the Zbig is proportional to T cubed. You can imagine. So indeed, we can obtain the T cube behavior in, for example, aluminums. So this is temperature dependence of Zbig. This behavior is S over T is proportional to T squared. This means that this is proportional to T cubed. And we also have the Honan-Black. This behavior is T cube behavior, and we have the maximum around here. This is the same temperature dependence as the gold, silver, copper. Yeah. So the characteristic temperature is around 50 kelvins, so very, very low temperature. This is a characteristic feature of Honan-Black. So in semiconductor case, we can get these equations. So yeah, I skipped the details. So if you would like to know the details, please ask after this seminar. So anyway, the Zbig in semiconductor case proportional to this equation, tau Honan. Tau Honan means that the reaction time of Honans. So yeah, this one. So when we see the experimental result, this is the experimental result of iron antimony 2. So we have the peak at low temperature. This is the Zbig coefficient, and the peak at low temperature. This is coming from the Honan-Black. And the important point is that so we have the sample size dependence. If we use a large sample, in this case, the Zbig is large. And in this case, the kappa also more large. We have sample dependence, sample size dependence. So the thermal conductivity of kappa is expressed by these equations. This here is a specific heat of Honan, and this is the velocity of Honan, and L mean that the mean free path of Honans. This is coming from the size of Honan, size of samples. Therefore, we use a large sample case, we can get a large A, and finally we can get a large kappa. So, and then the Zbig also have this tau. Tau is proportional to size. So therefore, the large size case, we can get a large Zbig. So this behavior is coming from the sample size. So the important point is like this. So in semiconductor case, we have the sample dependence in Honan-Black. So okay, And so the future of Honon block is a large civic. So maybe this is the most large experimental result of Honon block. This is not the civic. This is just a Needles effect. This is a transverse effect. But the amplitude is around 1 volt per Kelvin, very, very large effect. So if you use a large, maybe this is a large sample and the very pure samples. So if you use a large sample and pure sample, you can get a large voltage by using Honon block. So this recently there is a package to calculate the Honon block contribution. So this is called the ELF-Volt. This is not my my studies. This is maybe US groups. So anyways, recently many groups are trying to calculate the Honon block contribution by using the band calculation and or combined with Volt quantifications. Maybe global competition package development. Yeah. So this is the theoretical result of the silicon case by using this package. So red point is experimental result and the black one is theoretical result. Yeah, very consistent with the experimental result. Yeah. So if we apply the temperature in magnetic, in non-magnetic case, when we apply the temperature gradient, we can get the heat flow from electron and the heat flow of Honon. But in magnetic material, we have the additional heat current. This is a magnons, heat current of magnons. So this figure shows that the heat flow of magnon. And so when we have the magnon electron interaction, in this case, we have the additional the origin of the thermoelectric effect. This is a magnon block effect. So magnon block effect is originally suggested by theory. The BRIN suggested this magnon block, and partly maybe the iron has a magnon block effect. This is partly observed by the Bratt. So this is an experimental result of iron case. So yesterday I talked about this. So this black point is experimental result, and this line is a magnon block effect, and this solid line is a magnon block plus Mott formula. Mott formula is coming from the diffusive effect. So very consistent, therefore the House state. This one is coming from the magnon block. So we show that the Honon block materials. So number one is simple metals. Number two is a doped semiconductor case. For the magnon block case, we showed that iron case and cobalt nickel also has a magnon block like this. But we don't know the magnon block materials in magnetic semiconductors. Maybe this material has a large Zeebeck because in this case, we have the large Zeebeck and large power factor. But we don't know the good candidate material. But recently, no typical material, but recently we found good candidate materials. So this is the, we have two candidate materials. One is a chalcopyrite. So the second one is iron tungsten doped iron hoistlers. Yesterday I took this one. So this material has a large Zeebeck at around room temperatures. And so especially in this case, we have the large power factors. So this power factor, this amplitude is located here. This amplitude is larger than the potential materials. Okay, firstly, I talk about the chalcopyrite. So this material has an antiferromagnetic state. So below 823 Kelvin, so this material has antiferromagnetic phase. And this in this phase, this material is a semiconductor. The band gap is about 1.5 EVs. So you can get this material from nature. So we can get this material in this is in Japan. This is Arakawa Poisons. So now is closed closed, but we can get this chalcopyrite here. So you can get we can get chalcopyrite in the hydrothermal vent. Maybe you know that how to say boiling price in sea. So maybe you can get this material in here. So recently, our collaborators found the large sum azidic in calcopyrite. Especially this material is coming from the deep sea hydrothermal vent from here. So and they measure the Zwick and get at that time we can get a large Zwick. Maybe this material has an impurity band. This is schematic picture is electric state, and this is a conduction band. We have the impurity band. Maybe this is coming from the impurity band, but the board quantification does not adequately discuss the contribution of impurity band. Therefore, we need the microscopic theory to discuss this Zwick effect. So this is a microscopic theory. So we use this one. So maybe as I said, the Zwick coefficient is defined by this equation. We need the L11 and L12. So by using the microscopic theory, by using the Kubo formulas, so we can calculate the L11 by using this Feynman diagrams, this mathematical method. And then using the Kubo-Latinchez formula, we can get the L12. The schematic picture is like this. So this is a mathematical method to get the L12s. This is the Feynman diagrams. So as discussed yesterday, we have many heat current in solids. So we can get many heat current in microscopic theory. So we have, this is a list of heat currents. So we have the heat current from the electrons, from the impurities. This electron-Coulomb interaction, we have the two-part, and from Coulomb interaction also we have the two-part, and from heat current from honons, heat current from magnons. So there are many heat currents in solid. But the important point is we divide the origin of thermal effect like 3 parts. So one is the diffusive Zwick effect. So second one is the drag effect. The third one is unknown, the unclear ones. So as we discussed many things here and here and here, so by using microscopic theories. So today I would like to focus on these ones. So this is a mathematical method to calculate the L12, especially in the Honon-Black case. So very complicated, but result is like this. So L12 is expressed by these equations. So we have the information of electric state, and we have the information of the Honon part. Yeah, we can calculate by using this one, and we can get the L12 due to Honon-Black. So this is a theoretical result, and this red line is a theoretical result. This one is experimental result. We can, the theoretical result consistent with the experimental result. Of course, we have the deviation from the experimental result because we only consider the Honon-Black. We don't consider the electric heat current of electrons. So maybe we have the additional terms. So we don't consider the detail of the bond structure. We use free electron systems. Maybe the deviations coming from these approximations. So, but the important point is the amplitude are the very same, and the temperature dependence is very same. So therefore, maybe this experiment is coming from the Honon-Black. And then so we can calculate the Magnum-Black effect by using the microscopic theories. So this is the calcopyrite result. So this one is the experimental result of calcopyrite. And this blue one is coming from the electron heat flow from electrons. And I'm sorry, black one is a heat flow from electrons. And the blue one is coming from the Magnum-Black. And the red is the total of the Zwick effect. So the amplitude is very same as the experimental result. Maybe this experimental result coming from the Magnum-Black. And then, yesterday I talked about this one, so I skipped this one. So I talk about the dragging effect, and I have a time. No time. Okay, I skipped the final one. So I prepared this as yes, film substrate system, but I skipped this one. I show that slide. And if you would like to know the details, so please ask me.
Okay, thank you very much, Professor Matsura, for the
This is
nice
summary of my
presentation.
talk.
Yeah, so for those who have questions, you can type down your question in the chat column. Then I will read the questions after the second speaker. Bagi Bapak Ibu yang hendak bertanya, dipersilakan untuk menyampaikan pertanyaannya pada kolom chat. Boleh dalam bahasa Indonesia, nanti bisa saya terjemahkan. Terima kasih banyak sebelumnya. Okay, so for the second speaker, we have Dr. Dita. So, same as the first presenter, you will be given 30 minutes. And if there's 3 minutes remaining, I will remind you by giving this sign. So, yeah, you can see from your screen. And before you start, I will read your CV. So, Dr. Dita is now an assistant professor in Sibaura Institute of Technology before she earned her degree in physics from Institut Teknologi 10 November Surabaya from her bachelor and master, and for her PhD, she did that in Osaka University in condensed matter physics as an experimentalist. So, Dr. Dita will give a presentation entitled Doped Organic Superconductor and Magnet Probe by Muon Spectroscopy, or superkonduktor organik terdoping diuji dengan spektroskopi muon. So, Dr. Dita, please get started.
Thank you very much. Can you hear my voice clearly, or should I mute my? Should I mute?
I can hear your voice.
Okay, it's fine, right? Okay, thank you very much for the opportunity. My name is Dita Putrisari. Excuse me. Pakai itu tuh udah bisa. Oh, okay. Sorry. Thank you. Can I continue? Okay, so here is title. Thank you for the introduction. And here is my collaborators, mainly from the USR experimentalists and the organic conductor scientist in Japan. And also I collaborate with Watanabe-san's group in Riken. Okay, before I present my study, I would like to introduce my university where I belong to. So I belong to Shibaura Institute of Technology in the Innovative Global Program.
Excuse me, could you please open your camera? Sorry.
Oh, okay, sorry. Yeah, so Innovative Global Program in Shibaura Institute of Technology is a research-based international undergraduate program. We have the computer science group, physics group, where I belong to, chemistry group, and humanities group, and we can connect to the graduate program, to the graduate school for engineering and science. So from the undergraduate program, the student can choose their laboratory from the first year. Yeah, we are quite diverse member. Okay, so SIT is Shibaura Institute of Technology, founded in 1927. It's a private university in Tokyo. We have 2 campuses, in Omiya campus and Toyosu campus. Yeah, in Toyosu campus, it's in the left side, and in the right side is Omiya campus, where there is a laboratory of physics in multiple extreme conditions, the laboratory I belong to. Okay, maybe it's enough for the introduction. So let's see my contents today. So I would like to introduce for you the organic metal. What is the organic means? Actually, organic is the carbon-based material. And I have the metal, organic metal, and I have chosen the one of the organic material, so-called kappa 84 mercury chloride system. And then I will introduce the muon spin relaxation rotation spectroscopy, and I will show you the result. Okay, so yeah, just from the simple picture of metal, maybe this is very, like very simple explanation to show what is the conductivity. Is actually a flow of negatively charged electron. When flowing, it has resistivity, but the electron is actually scattered in the material. Okay, then I introduced the concept of mode insulator that if we have one electron per side in the good lattice of material like this. So in this case, we have the concept that the material should have the metallicity, but the conditions when we measure the resistivity, it's become insulator. So what's happening here is so-called mode insulator. The insulating state is caused by the strong electron-electron interaction when the system is half filled or one electron per side. So we have the competitions between the kind of kinetic energy, the first term here, that electrons is hopping, and the kind of potential energy from the Coulomb repulsion. So the competitions between the kinetic and the potential-like energy. So when the T or the kinetic energy win, we have metal. When the potential energy win, we have insulating in the mode insulating state. Okay, but then we need to remember that the electron is the origin of these situations, but the electron actually has charge and has spin, right? So the spin and charge are indeed joined together into physical one electron. By theoretically we have like a physical electrons. Physically, we have a join between spin and charge by line or flux, or if we see it discretely as a quantum. Yeah, that's a one way to see, to explain the differentiations of the spin and charge, even though we have one physical body, like a particle as an electron, right? And then if we have a spin, if we see the electrons have mass, spin and charge, but in some circumstance, spin and charge can move independently. So if we see only the spin, maybe if one spin is flipped like this, and then if it will change, it can diffuse, or it seems to be moving. So the spin is moving like this. Or if we remove one electron, so this is more the different charge inside around the other. So maybe we can see the charge is moving. Okay. So sometimes we need to see the spin and charge behavior separately, because the measurement cannot. Sometimes measurement is only spin sensitive, and measurement can only be the charge sensitive. Okay. Right. So in the case of mode insulating state, we can make the mode insulating state to be metal. So one of the ways is to remove one electrons, or we call it a doping. Yeah, we can remove one electron, or we add one more electron. Then finally, there is a movement of electron. Or we can pressurize the mode insulating state, then it become metal. Yeah, so it means that we tune the competition between the potential and kinetic energy. Okay, so we can pressurize the mode insulating state to become metal. Okay, and in the organic metal, the condition is more the second one. So you can see here from the mode insulating state to the metallic state by pressure, there is a transition from a mode insulating state to the metallic state by pressure in the organic conductor. It's in usually. Okay, so yeah, if we have mode insulating state, and then if we pressurize it, it will become metal, or it's usually modeled by a Fermi liquid model. And the resistivity will, we have this temperature dependence of resistivity. And Fermi liquid is usually temperature square of resistivity, follow the temperature square of resistivity. Or if we dope the mode insulating state, we can also have the metal finally to be like this. But before it's being the normal Fermi liquid, it seems to be not Fermi liquid, because we found some deviations from Fermi liquid in the organic metal. So yeah, that is the charge situations. In the spin situations, the organic metals can have the opportunity to tune the lattice from the so-called square lattice here, if we have such kind of lattice, but we can tune because of the softness of the organic material, we can have the square lattice or triangular lattice. So in the way of the triangular lattice can be formed, the spin, maybe we can have the spin unordered. Okay, so because of the geometrical frustration, so the spin cannot decide which directions to be ordered. Okay, so organic has the advantage to have the variety of the magnetic state. Okay, so how the organic can have such kind of things is because this is the we have the molecule, but many molecule arranged in a good way. I think it's beautiful pattern, something like this. So in the one dimer, we have one electrons, and then it can be triangular or square lattice like this. Okay, so the this conducting, we call it dimer here, is in the conducting layer because it has a layer of insulating and conducting layer. So we have this kind of structure in the organic metal. So I choose one organic metal, which is a little bit strange because of the how can I say, the situations of in this conducting in this material, it has the triangular lattice like this. So perfectly triangular lattice in the dimer. So yeah, this is the crystal. Yeah, then for the resistivity, it has some how can I say? It has the non-Fermi liquidity because the N value here, the temperature dependence of the resistivity is linear, and then by pressure it's become 2. So here is the resistivity behavior from 1 to 2. Okay, so the usually organic is half filled, 1 electron per side, and then this one is there is a typical triangular lattice sample, which is kappa ET2CU2CN3. This is a weak pressure induced superconductor. I mean, this is insulating, but by using little bit pressure, it's become superconductor. However, in the material that I will introduce, there is a self-doping in the material so-called kappa mercury brome. And then it also has the non-Fermi liquidity. So here is the material. So you can see kappa ET4, mercury 3 minus delta bromine 8. So there is some incomplete stoichiometry of mercury here due to the incommensurate lattice in the crystal structure. So there is some kind of mismatch. So the unit cell is repeated normally, but the mercury metal here, maybe there is a little bit mismatch, so it cannot be perfectly 3. So it's kind of 3 minus something. So this is the doping. So it's become a doping system. So the this material has the doping situations, but also can be easily tuned by pressure. Okay, right. So there are two materials here. So here for easy, I call them mercury brome, which is metal, but it becomes superconductor by reducing the temperature, by cooling down the temperature. And the other one is mercury chlor. So the changing is only brome and chlor. Okay, but only changing one atom, we can have another ground state, which is metal to insulator. Yeah, it's probably not insulating state. Okay. Yeah, so mercury brome and mercury chlor. Mercury brome is superconductor, mercury chlor is insulating, but both are metal in the high temperature. Okay, so I start from the mercury brome because it has the triangular lattice as I showed before, and the spin characteristic of this mercury brome is similar to the quantum spin liquid, the other quantum spin liquid system, organic system. So it's a very, how can I say, suspiciously, maybe this is originally spin liquid, but due to the dop, situations, it's become metal and superconductor. So it's a candidate of doped spin liquid. And then in the low temperature, probably there is an antiferromagnetic spin fluctuations, because this is the origin of the non-Fermi liquidity sensed by the resistivity measurement. Okay. Then, okay, so both mercury brome and mercury chlor indicates the antiferromagnetic spin fluctuations because the system is close to the so-called quantum critical point, so the QCP, because the how can I say, in the low temperature, there is competitions of the superconducting state and quantum spin liquid state. And then this is the situations only determined by temperature. Okay. Okay, so the superconducting state nearby that kind of quantum criticality is hard to model by theory. So that's why I need to I need to study by experiment result. Okay? Then we can focus on the non-Fermi liquidity, the charge situation, and spin liquidity in spin situation in this mercury brome and mercury chlor by mu-SR. Okay. So yeah, what is mu-SR? We need muon. Yeah, so mu is the muon. So mu here is the abbreviations of muon. So we can produce muon by using accelerator. Yeah, so we need a proton beam, and the proton will hit the muon target. It's carbon nuclei, and it will produce pion, and the pion will quickly decay into muon. So muon is very 100% polarized due to this conservation nuclear energy reaction here. So muon has mass, muon has charge and spin. Okay, and muon is very sensitive. Sensitive by means that the geometric ratio is so large. So only few Gauss of the magnetic field can make the muon precise. Okay. So if we have the polarized muon beam here, then we hit the muon beam into our sample anymore. So we will have asymmetry with polarizations. We will have a muon that is scattered, not in the 100% one directions. And then we can count the asymmetry of the positron, which is the decay of the muon, in the forward and backward counter. Okay, so we can count the how many positron in the backward and the forward. Then, okay, if we have some system which unordered spin in the usually in the high temperature, we will see this typical symmetry, okay, asymmetry curve, okay, the so-called Gaussian Kubotoyabe. Or if we have the spin, but it's random, we will see such an exponential term. So we will see like a decay like that, the muon spectra like this. Oh, I'm sorry, please ignore this. So it's only zero field mu-SR. And if we have long range ordered, magnetic ordered like this, for example, this is antiferromagnetic up-down spin or long range ordered, we will see the muon will precess, then we will have the cosine functions, okay, without any additional external field. It's only from our sample. So magnetic field is only from our sample because of long range magnetic order. So that is typical spectra that muon that mu-SR if you do the mu-SR experiment. Okay. Okay, so that is the introduction. So I will go to the result. So actually, we can measure magnetizations of the sample using squid magnetometer. Although this is kind of a more bulk measurement, I mean, it's not microscopic measurement. So yeah, this is the magnetometer that I use. The sample can be set like this. This is the single crystal that we put in the straw. Okay, so for the brome, so you can come back to the brome and chlor sample. So this is the typical curve. So when we cool down the temperature, it will have broad peak like this, and it will best fit by the model, triangular model. Yeah, it's as we expected. Okay. But for the chlor, it is a little bit in between triangular and square lattice. Maybe this is not perfectly the triangular lattice, so it's a little bit shifted to the square lattice. You can see this in the 120 Kelvin energy. So this is in between the triangular and square. Okay. So that is the, we confirm the triangular lattice of the brome and chlorine sample, I'm sorry. Okay, then we measure μSR to see more detail, okay? So this is the crystal, we need much more mass of the sample for μSR measurement. So in total about 100 milligram. For the squid, we only need like 7 milligram, okay? So I put, imagine that I put my sample here in the spectrometer that I showed in the schematic figure, okay? And then this is the spectra. You see there is a exponential term, exponential shape of the spectra, both in the brome and chlor, but there is a, maybe we see the different later, okay? So from the brome, there is no difference between the spectra above the superconducting temperature to the crossing the superconducting temperature. I mean, it's the same spectra above and below critical superconducting temperature. But for the mercury chlor, we can have the hint that there is no long-range magnetic order, yeah, because we don't see the muon spin precision. Okay, then if we plot the parameter, the relaxation rate, so we see here the metal to superconductor for brome and the metal to insulator for chlor. So at the high temperature, the situation seems to be the same, but the ground state is different, and muons show the different temperature dependence. You see, this is just flat, but this is increasing, and yeah, we have a broad peak here. So in the mercury chlor, increasing of rate below 1 Kelvin might be related to inhomogeneous spin state. Okay, that is you can see also this is the resistivity, the charge situations. This is changing from metal to insulator transitions, and we see a plateau in the relaxation rate, μSR relaxation rate. Yeah, then how is the behavior of the conducting electron? So-called NMR night shift can sense the magnetism from the conducting, can sense the situations of conducting electron. However, previous studies show that there is a heterogeneous hyperfine coupling, so NMR is doubtful. So we would like to try the μSR night shift. I'm sorry, how much time do I have? 7 minutes, okay. Right, so this is the muon night shift measurement. So I need a very high field, external field to be introduced in order to see to sense the magnetism if we have magnetism in the conducting electron. So this is the schematic of high transverse with μSR. Actually, it's the same. We have counter, but how can I say? Muon is conditions to be rotated 90 degrees, so we can have the transverse field, external field up to 6 Tesla. And then we can cool down to 2 Kelvin, from 300 to 2 Kelvin. Okay, this is the spectra for the chlor and the bromine sample. And maybe easier for you to see if I plot with the rotating frame, because this is 6 Tesla, it's very difficult to see without the Fourier transform. So I can show you this Fourier transform after the transformations. So you can see here for the brome, there is no shift. Like, I mean, if you compare with this central line, it's almost the same spectra for the brome, but for the chlor, you see there is a shift by lowering temperature here. Okay, so the peak here shifted to the right side. Okay, if I plot, so it should be like this. So for the chlor, so there is a gradual shift by lowering temperature, but for the brome, it's barely changed. Then we can compare the situations of night shift and the susceptibility that we have. So I will plot at the same temperature, the night shift versus the susceptibility here. Okay, like this. So for the brome, we cannot see such a obvious difference. But for the chlor, we can see a difference here, and we have deviations from the linearity. So yeah, maybe this is if we have the Fermi liquid situations, it will have like only linear, but there is a deviations. So maybe this is related to the non-Fermi liquidity. of the chlor. But then we can also sense the muon Haber-Van coupling constant to be 282 from the slope. Okay, 282 air state. And then assuming double field calculations, I assume there is a magnetism in the site. So this is the muon site from the our calculation, DFT calculations. And we estimate that for the chlor between the chlorine site and muon site, the Haber-Van the double field is around 279 Gauss. So we think that this is comparable with the night shift. So maybe we can conclude that the we can conclude that the night shift can sense the magnetism. Okay, so the night shift and light. Okay, I plot also the line widths and the night shift, the line width of the spectra. The night shift and line widths gradually change, crossing the metal insulator transitions. If the night shift is originated only from the electron charge, there should be a jump because we have metal insulator transition, but it's not. It's like a gradual change. So maybe the night shift is originally from the magnetism of the conducting electron. So this is consistent with the double field calculations. So yeah, this is my summary. So at the high, we confirm that there is antiferromagnetic exchange interactions, and then there is a from zero field μSR, there is no long range order for the chlor sample, and the ground state seems to be a spin freezing because there is no muon spin precession. But it's unconventional because it's coming. It started from the metallic state, which is strange, and then from the high field transverse field, we argue that there is a contribution from the spin. Yeah, in the importantly, μSR can capture both a spin and a charge magnetism from the conducting electron. Yeah, so the next step is actually to sense the spin diffusions by longitudinal field μSR to sense the quantum spin liquid idea from the beginning. Yeah, there will be a talk tomorrow. It's still series of our workshop, so please, yeah, keep up with us. Thank you very much. Oh, I'm sorry. I'm sorry, I don't have the rhyme, but I will show a typical physics joke. A neutron walks into a bar and asks, "How much for a cup of coffee?" The bartender smiles and says, "For you, free of charge." Thank you very much.
Thank you very much, Dr. Tita, for the nice presentation and the jokes. Yeah, it's time for the question and answer session. As I already told you, you can write down the question in the chat column, or you can raise your hand, and then you can talk with the speakers directly. But before that, I would kindly ask your cooperation to fill in the attendance list. So it's already in the chat column. So there's a time limit for filling in the form. It's until 11:30. And the certificate would be sent through email. So please also write down your email. Bagi Bapak Ibu yang hadir pada webinar kali ini, mohon berkenan untuk mengisi daftar hadir yang sudah dibagikan pada kolom chat. Waktu pengisian dibatasi sampai 11.30 WIB. Nanti sertifikat akan dikirimkan ke alamat email masing-masing. Jadi mohon untuk disertakan pula alamat emailnya pada lembar absen. Iya. Baik, di kolom chat sudah ada satu pertanyaan. So there's a question from Maida. So he said, "Thank you." And the question I think is given to Professor Matsura. Is the phonon drag and magnon drag in this term treated as a quasi-particle? I will repeat the question. So is the phonon drag and magnon drag in this term treated as quasi-particle?
Quantum black, can you hear? Quantum black is just a phenomena. This is not the quasi particles. So we use free electrons. We have a free electron and the phonons, and we have the interaction between the phonon and the electrons. So of course we have the interaction. So therefore we have the mixed state of electron and phonon. So maybe, of course, we can say this is a quasi-particles, but in my theory, I use just free electrons. Therefore, this is not, a phonon black does not mean that quasi-particles. Yeah.
Yeah, thank you for the answer. And following your answer, I was thinking that do you also consider the magnon and electron interaction?
Yes. In the phonon black case, we use interaction between the phonon and electrons. The magnon black case, we consider the interaction between the magnon and electrons. But the magnon case, we have also magnon is coming from the spins. So therefore, we have the interaction between the spins of the localized spin and the conduction, the spin of conduction electrons. This is a magnon electron interaction. Yeah.
Yeah, so since there is no question yet, so I will follow up your answer. So the magnon will interact with the spin of the electron. But
Yeah, magnon.
also,
So please imagine so we have the localized spin and the conduction, localized electron and the conduction electrons. So localized electron has a spin, and the conduction electron also has a spin. And okay. The conduction localized spin is like this, and the conduction electron is like this. So we have the interaction here. So this is electron-magnon interactions. Magnon is just this kind of behavior, but we have other images like this.
So it's only interacts with the spin of the electron. How about the charge of the electron?
In this case, this interaction moves this interaction is the origin of the drag effect. Just we can get the movement of the electron by using this interaction because we have the temperature gradient. When we apply the temperature gradient, in this case, we can get the heat flow of magnons. And then so we consider the interaction between the electron spin and magnon spin. In this case, the electron moves. So finally, the electron also has a charge, not only spin but also charge. Therefore, we have the unbalance of the charge in samples. Finally, we can get the voltage.
Okay, so that's such complex interaction. Okay, thank you very much for your answer. And let me see for other questions. Okay. So we have Dr. Eddie in the room, so you can open your camera, perhaps. Yeah, thank you.
Thank you very much, moderator, for the opportunity. I will ask question to Mas Rasal. As I understand from your explanation that we have two methods to calculate thermoelectric properties from then
bandage ring and
also drag effect. And if we want to calculate thermoelectric fully from quantum mechanics fully, we should use a Kubo-Luttinger, and how this Kubo-Luttinger can handle the higher temperature, because in the optimization only available in the lower temperature.
Kubo formula, the quantum formula is has the exact formula. We can use all temperature regions. But in my model, I consider only the low energy state. Therefore, we can consider only the low temperatures. If we consider the full band structures, we can calculate high temperature region. Not only the heat flow from electron, but also the drag time. But the drag time, to calculate drag time, it is in how to say, there is many interactions, many integrals. So this is the how to say difficult to calculate. But I use how to say analytical calculations to calculate the integrals. Therefore, I can calculate. But when we use numerical studies, in this case, maybe you have many integrals, so it is very tough work. Yeah, therefore the how to say. So we use many approximation. In this case, you can, for example, you can get the low temperature region, but high temperature region, maybe you cannot good answers because you use many approximation. Yeah.
Okay, thank you. And one more question. And in the drug, is it how to calculate tau, electron excitation time?
Now,
Can we?
this how to say you mean the drug case?
Yeah.
Drug case is how to say, for example, the electron time electron is coming from the electron Hono interactions. Yeah, therefore, if you use you can calculate the tau, but Hono drug is usually we calculate the tau is the Fermi Fermi golden rule, but drug is a special phenomenon. I mean that the drug is just a momentum transfer between the electron and phonons, and we consider the in an equilibrium state of phonon. I mean that how to say the momentum is transfer from electron, and we also consider the go back momentum transfer from phonon to electron. So usually we consider phonon is equilibrium state. At that time we can get, for example, the how to say, the usual resistivity behavior. But and Hono is a very special phenomenon. Therefore, it is difficult to estimate the tau. Yeah. This is how to say essence of Hono. Maybe you understand the essence maybe for Hono. Yeah.
Yeah, thank you.
Thank you very much. Okay, yeah, please.
So, so how is your comment about the non-fermi liquid state that I mean, because sometimes we don't always have the fermi liquid state. Maybe you can have some, because we can start from the Boltzmann equations, but maybe for the non-fermi liquid, maybe the collisions is much more, how can I say, we should not ignore the individual collisions.
For example, in your case, so you use the kappa broke case. This material shows that non-fermi liquid state.
Yes.
And in my memory, that this material shows that the strange thermoelectric effect. Maybe Canada's group shows that recently Canada's group 2 years ago or 3 years ago. Yeah, at the time the house state, the resistivity is linear, but some thermoelectric effect is maybe log behaviors.
Okay.
And so, for example, when we consider these phenomena, we use of course we use a microscopic theory, but especially we use for example fluctuations. Especially we focus on the special phenomena and we calculate this kind of behavior. This is not for example, in this case, for example, in your case, we neglect after, for example, Honon lag and Magnon lag. Just we focus on your fluctuations.
Oh.
And in this case, we can calculate.
Yeah. We can if we cannot see the whole picture, but if my measurement can focus on the spin fluctuation, your theory can
collaborate.
So we discuss.
Thank you very much for the discussion. Again, I would remind you, for those who want to have question, you can fill in the chat column or raise your hand. There is someone raising hand. I don't see it. Okay. So, Mr. Jumaida, you can raise your question.
Okay. Thank you. Thank you. Thank you for Dr. Matsuda for answering my previous question. But now I want to ask to Dr. Tita. about the mu SR a measurement. So I'm a new in mu SR, but I'm experienced in the single crystal. That in my case, in the strongly correlated system on the cerium, that if we use method flux, we just have the small amount of a single crystal, like maybe around two milligram. So I saw in your slide that maybe you have also small single crystal. So my question is for the mu SR, how we what trick to measure mu SR, but we have only small amount of single crystal. Thank you. I'm sorry. Could you unmute?
Yeah. Can you hear me? Yeah.
Yes.
Yeah. Thank you for the questions. Yeah, you have a point because I also show this for advertising MUSR, but your question is how the trick, right? So there is no other tricks rather than we produce many sample. Okay, so we need to produce more than 100 milligrams because that is the minimum necessary for measuring pulse MUSR. There is another MUSR type, so using BC muon. In that case, less sample is okay, but it's still 50 milligram or 30 milligram. So you need to align your single crystal like this. I align one by one the single crystal I have, and then stack them in order to have the good thickness for doing the MUSR.
I'm sorry. So how about the orientation? So we neglect the orientation of the crystal? Or...
Yeah, for my case, the layered structure give us advantage that the flat surface, you can see this is the this is the XRD, the tip of XRD, single crystal XRD measurement. My oriented crystal is like this. So BC plane is the connecting plane. So it's plate-like is the facade of my plate is the conducting plane. Of course, I have a degree of freedom of the BC, but it's the same, right? So it's still in the conducting plane, but at least I have the facade of conducting plane, and it's the same in the conducting plane. So if I applied the field perpendicular to the plate light, it means that I applied the field perpendicular to my conducting plane, BC plane. Yeah. So you can consider your own axis. Yeah.
So how about to determine the in your case in BC plane? So you measure all of them, or you measure all of them and use after that you stay.
Okay, so I can distinguish the crystal by eye because it's very good shape. But we need to check the several crystal by XRD, and then we can confirm that the flat facade is the connecting BC plane, as you see here.
Oh, I see. So not every crystal you
I think you can distinguish. Yeah, I think we can distinguish. Yeah, because we can have the good age. So this is a typical of my sample. There is something like that. Yeah, of course this is more than one time, but yeah, I did several. You can use the fast scan, so you can confirm the lattice constant. Yeah, fast scan of the XRD, X-ray diffraction measurement. So it's enough to you can confirm your lattice parameter. It's only 5 minutes if you have access to such a measurement. But one measurement, you need to have the complete measurement, and then you can reconstruct the crystal structure. But for checking, you can use the fast scan.
Fast scan. Oh, I see. Yeah. Last question. How to grow this single crystal? Is melting or?
No, this is from the
Oh.
electrochemical
Oh,
oxidation.
electrochemical oxidation. Oh, okay, I see.
I will talk about more tomorrow. Yeah, for the
Tomorrow.
organic. Yeah.
Okay, thank you. Thank you very much.
Okay, that's such a nice discussion. I will follow up this discussion. So technically, for organic molecules, I was imagining that it would have like a higher degree of freedom for rotating. So I was thinking for one single crystal is different with others. So how do you think about the reliability of the measurement results?
Yeah, thank you very much. So we have a typical shape. So one is the plate-like, or we have the needle-like. So we need to have the good shape. So the organic crystal, one of the advantage is we can reproduce, if we have the good conditions, we can reproduce the product and we can see by eye. But of course we need to check by XRD. But the shape itself easily can be distinguished by the shape if under the microscope. Yeah. So reliability, one is XRD, we need to confirm, but then we can see the morphology. Yeah. Because it's very different. One is plate-like, the other one is needle-like, and the other one is like rectangular. So yeah, I will also do it. Maybe tomorrow.
Okay.
But maybe you can imagine
I see.
Yeah, it depends on. Okay, let me explain here. So this is okay. Unmute.
Yeah.
Oh, sorry.
Yeah.
You can see here. This is the dimer. Yeah, two molecules and have one electron confined in one dimer. But this is, you see, 90-degree related, like this and this, and yeah. Yeah. The other has side by side. So we have several type. So here is kappa, but we have lambda, theta, and others. Yeah, it's determined by the arrangement of the molecule in the conducting plane. Yeah, it's one of the advantage of organic. Yeah, and yeah, maybe you think that it will be some unstable. That is also a good point. That's why we need to do the measurement in the slow cooling flow. So from the high temperatures, in order to avoid randomly ordered of the ethylene group. So we have ethylene group here, so the CH molecule. So we need to cool down slowly from 300 Kelvin to. That's very typical. Yeah.
Okay, thank you very much for the answer. And still in this slide, I mean, in your system you have triangular and square systems, but from the experiment results you have only one peak corresponding to each feature. So I was thinking both are present, but why only one?
Okay. So could you mean this one? Yeah. For the triangular lattice, this is the peak, but we have the peak and the positions of the peak and also the amplitude of the peak. Not only the one peak or two peaks. So for the triangular lattice, with the electromagnetic exchange interaction energy around 130 Kelvin, we have this model. So the peak will have, how can I say, the peak at 30 Kelvin, and the absolute value is about this one, 0.9 10 to minus 3, something like that. So it's peak simulated, determined by the simulation, and it fits with our experiment. But for the mercury core, it's not fit with the triangular, right? But we also have the square lattice model. And the square lattice model, when we set the exchange interactions to be 125 Kelvin, you see the ground here, and then the dash ground here. So it's the data seems to be in between 125 Kelvin.
So in between means both are present, or?
Yeah, maybe. Okay, there is an anisotropy. Okay, I show this one. Probably there is a little interactions for making this one. You see, if this is extremely only the green, so we have square lattice. But we have the dashed line become the same with the solid line. We have square. But if this is a little bit weaker, maybe we have anisotropic triangular lattice. That's why I said in between triangular and square.
So can I say that the experiment results give you the dominant lattice?
At this moment, I don't know. I don't know which one is dominant. But compared to the broad, I mean, we can compare to the sister compound. It's still the broad peak, but it's just not the triangular lattice. And that's why we may see the freezing of the spin. I don't see this is the same, maybe quantum spin liquid. Maybe there is some freezing that is consistent with our MSR. So there is a broad peak. Even if this is very low temperature, it's 0.1 Kelvin. So the increasing of relaxation rate about 1 Kelvin indicates that we may have some slowing down of the random spin to be ordered in some way. But then it's a very broad. We found that it's decreasing. So maybe this is freezing. Yeah, the spin starts to freeze in the random situation. It's not long range order because we don't see neon spin precision. Yeah. So that is why maybe it's consistent with not triangular lattice. Maybe if it's triangular lattice, we will see only under ferromagnetic spin fluctuations, and we'll never see the decreasing of the relaxation rate. Yeah. Maybe, yeah, hopefully like that.
So we still have 7 minutes. I will let the audience raise the questions. Yeah, you can talk directly to the speakers or write your presentation, your questions in the chat column. It's also can be done in Indonesian language. Ya, bagi Bapak Ibu yang ingin bertanya dalam bahasa Indonesia, boleh diperkenankan. Okay, if not, I have a simple question about the heat current produced by magnon to Professor Matsura. So I was thinking, is every single magnon can carry heat current? Or there is a requirement for
Magnon
what
has
kind of?
if we apply the temperature gradient. In this case, we have the magnon heat current of magnons. Yeah. For example, the ferromagnetic magnon also has a heat current, and ferromagnetic magnon. Yeah, we have the heat current of antiferromagnetic magnons. Yeah. For example, another spin structure also has this kind of heat flow. Yes.
Okay. And this is quite naive question. What is the meaning of negative feedback coefficient? There is positive and negative.
In that Zeebeck coefficient. The sign of the Zeebeck is corresponding to the sign of electron or holes. The negative case is corresponding to the carrier is electrons, and
Okay.
positive is corresponding to the whole carrier is whole.
I see. I see.
No, but exactly speaking, this is depending on the band structure and the electric state. Therefore, yeah.
Okay.
Okay, sorry, so if there is a time, I can show the sample synthesis that
Yes.
you might ask.
All right. Sure.
Okay, so Mr. Jumaida, maybe you can see this is the electrochemical oxidations for synthesizing organic conductor on organic compound. So we have two molecules basically, an ion and a cation. It's just like salt. It's like a sodium chloride. So we have a positive ion and negative ion. So positive ion is from the positive molecule. Of course, it's actually natural, but when we combine them, dissolve them into a solvent, we will have some charge transfer. So we will flow the current like this. So then the crystal grow in the electrodes. You can see this. I also produce very small single crystal. So I need to repeat such a synthesis procedure for my SR experiment. Then from one batch, for example, you can see two morphology like this. Maybe this is question from Dr. Effie as well. So you can see there is a needle and there is a plate. Yeah, and this is turns out to be very different arrangements of the molecule inside. So for lambda, it's a side-by-side dimer, as I explained. But for the kappa, it's a 90-degree rotated dimer. But the facet is plate-like, but the lambda is needle-like. So you can distinguish. Yeah, maybe hope it's answer your question. Oh yeah, sorry. This is resistivity measurement. Okay.
Okay. Mr. Jumaida, did that already answer your question?
Yes. Thank you.
Okay.
Thank you for showing us.
Thank you.
Okay. Thank you for showing the experimental part. So in fact, I made a mistake. In fact, we still have 7 minutes. So we still, yeah, we still have time to discuss with our speakers. Please feel free to ask questions.
I'm sorry. I want to ask something about the non-Fermi liquid theory. Is it in this term? As we know that Fermi liquid is based on the Landau Fermi liquid, but in this term on the non-Fermi liquid, could you maybe explain about and how the theory to clarify this phenomena?
Yes, maybe I can answer from the experimental phenomenological viewpoint.
Yes.
The clear deviations is coming from the resistivity, temperature dependence of resistivity. Yeah, so as we know, we have, of course, another terms like the higher terms of the temperature dependence, maybe coming from phonon and so on. But the first term, the second term here, it's very, how can I say, it's important to distinguish the typical Fermi liquid. So T square, so the T square is the typical Fermi liquid temperature dependence of the resistivity for Fermi liquid material. But for example, it's firstly found in the high-TC cuprates, so the inorganic superconductor. The metallic state of that cuprates superconductor shows the T linear, so the N is 1. So that is the first phenomenological resistivity measurement indications of the we call it it's clearly not Fermi liquid, right? And then in our case, we also show we can also see such behavior. Here you see the N equal 1 here for the 0.48 gigapascal. You can see there is a linear, it's clearly linear like this, right? And then by pressure, it turns out that it's gradually changed from 1 to 2. So this is we can safely say this is non-Fermi liquid to the non-Fermi liquid, and then by pressure it's come back to the, I don't know, maybe come back or it's come to the Fermi liquid state. So for the microscopic theory, for me, I can answer. I think this is I cannot answer clearly, but as long as I studied. So the Fermi liquid means the electronic scattering is a kind of a long life, because the collisions, maybe Masura Sensei talk about the collisions modeled by the Boltzmann equations. We need to think about the collisions. For the Fermi liquid, the collision is kind of long-lived, so the resistivity is maybe different between n equal 2 and n equal 1. So for the n equal 1, the electronic scattering is much more short-lived. So electron is more easy to collide with each other. Maybe that is due to the quantum fluctuations and so on. But yeah, we can I can say short-lived and long-lived electronic scattering. But yeah, maybe Matsuro Sensei have another version.
Okay, thank you. So I want to ask one more. So this material is lies on the vicinity of QCP or
Oh, for me, okay.
or in
Yeah. Due to such kind of situations, because of the okay, sorry. Where is that? Here. Yeah. While the non-Fermi liquid, while the charge behave like a non-Fermi liquid, the spin behave similar to that of the spin liquid. The quantum spin liquid. There is a typical. Okay, I didn't show. There is a the well scaled of. I'm sorry. So I can show something. Can I show something? I'm really sorry. This is not my study, but there is a review study. I'm sorry. Can you see my screen?
yes, I can.
Okay. You paper. Where is this? Sorry. This one. So here is the susceptibility, the same with I showed, yeah. But you can see this is mercury brome, similar to my susceptibility data. But then the other is here, the right side. If we normalize the susceptibility data by J, the exchange interactions, you can see this is well scaled with the Kapasiu 2CN3, which is this is insulating quantum spin liquid candidate. So there is a spin state has the maybe quantum spin liquid, but it's very close to the non-Fermi liquid, because the chart shows like that, and it's also superconductor. So,
Yes, it's so interesting.
so that is the sense of quantum criticality.
Quantum criticality. Okay, thank you. Because I also have a similar situation in the cerium cobalt indium 5, which is if you apply pressure and they show it the superconducting system. So and maybe you have some antiferromagnetic constant. So it's so interesting. Thank you.
One more indication is the Clore system. I showed is metal insulator transition, right? So metal, but
Yes.
by pressure, it's also becomes superconductor.
Superconductor. Oh,
Yeah.
okay. So interesting. Thank you for the nice explanation. Thank you.
In fact, we still have 1 minute. Oh, no. Yeah, sure.
I do this out of the implementation environment. I will be continuing to the program that we have, but very positively to the office. What about what's about us thermal conductivity? Because when we take a step, if we take step back a little, when we consider electrons, we consider it as a barrier.
we can have a high seebeck coefficient when we have high charge carrier, but we then also have a large electron thermal conductivity, which is we do not want to. So what about magnon thermal conductivity, which I believe if we do have that one, that can negatively affect our power factor or ZT.
We have large limit and gives a large sample control. And also case also have a quick program, then we have a large limit change. In this case, the sample conductivity due to magnon is large.
Does it also can produce like large magnon conductivity? Magnon thermal conductivity. Magnon thermal conductivity. Thermal conductivity caused by magnon.
Is coming from the electron height of the quantum model. If we have a large lifetime of quantum model, in this case we can get a large Zedic and large Zedic with the quantum model and large Zedic of the quantum. The large mean part in that we can get large sample quantities. So therefore, if we have a large sample quantity, in this case we can get a large Zedic.
But when we consider our like ZT,
good question. The DT is coming from the S square sigma or kappa.
Kappa. And usually we consider
DT very small. Therefore, let's say the formula is the kappa is very large. I mean the sample that is coming from the leg, not only the leg, but also the common. So therefore, the however, I don't want to take the large sample conductivity to the whole temperature. In this case, the data is very small. But the magnon is very different. For example, I tungsten dot poison case. So in this case, the sample conductivity is coming from the electrons, quantum, and magnons. And maybe it's the sample conductivity is coming from the quantum and electron. But we have the actual sample conductivity is the magnets. This magnet is important to get large. So in this case, the kappa is not so large.
So like the comparison is like the seebeck coefficient compared to the kappa. The comparison is the seebeck still larger than the
kappa. It is on the sigma, right? Not so large, but we have the enough values. And the kappa is not so large, so this is negative. But the common large is the usual. So common large is does not have a large. Because we have a large kappa.
Yeah, thank you.
Yeah, such a nice discussion. You can follow up after this. Okay. So as a final reminder, there is an attendance list on the column chat. So you'll be given around 30 minutes after this webinar ends. So it's not filling in the chat column instead, but you click the link and then fill in the form. Okay. And before finishing this webinar, I would like to kindly request the speakers to close it with a closing statement. So perhaps because Professor Matsura is still drinking, perhaps I can start with Rita, because he's drinking. So can you start the closing statement? Okay, or Professor Matsura first. The closing statement, like summary or whatever you want to say, like or concluding remark or
concluding remarks. Not so. Yeah, thank you very much for listening to my seminar. So yeah, if you have interested in my seminar, so please ask to me. So yeah, let's collaborate, please. So thank you very much.
And for Dr. Rita, could you please give us your closing statement?
Thank you very much for your time, for bearing with me. My conclusion for the talk today is that GSR is one of the powerful tools, spectroscopy for sensing the magnetism, basically. But in some cases, probably also sensitive to the charge if we have the additional supporting data, something like that. And I didn't talk about the longitudinal fluorescence are today, but please continue to listen to our series of workshops, especially tomorrow. Thank you.
Okay, let's give applause to the speakers. Okay, I again would like to thank you for all the speakers and participants for your attention, for the attendance. And I would like to say sorry for any inconvenience, but because it starts with a rhyme, then I will finish it with a rhyme. Okay. Emma makes a friend with a dragon. It has a big eye and a long belly. This is the end of the session. I hope you enjoy the talks fully. So thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih buat Mr. Matsura dan juga buat Mbak Dita dan Mbak Evi yang sudah mengisi ornamat sesi ke-53 hari ini. Terima kasih Bapak Ibu atas kehadirannya. Sampai jumpa di ornamat berikutnya mendatang. See you.